Good morning, everyone. Today is April 15th, 2017, and this is the John Chappell Natural Philosophy Society Saturday Saturday morning science chat. So this morning we don't have any particular topics. It's kind of open. I suggested a few. Last week we had David DeHilster and Bob Nappy here explaining about the conference that's coming up, which is July 19th to 22nd. And that is only a few months away. Still haven't heard the particulars on the registration fees and stuff like that. So I presume that David is working on that. But I would encourage you all to come to the conference. I've been to one of the conferences when it was over in College Park. And that was quite some distance for me to go all the way over there in the East Coast. But now I'm on the West Coast, so now it's only like a 3-hour drive away for me from Seattle to Vancouver. So it's much shorter for me. But I would encourage you to come, and it's an opportunity to present your papers, or you can publish your papers, and to just talk with people. You can really get in their faces. Okay. And also, David encouraged everyone to take a look at the forums, and that's forums.naturalphilosophy.org. And we should have, if you're a member of the CNPS, you should have already filled out a bare bones version of your biography. And you can go, and we encourage you to fill that out and to start editing things. You just need to let David know that you would like to have right access to the wiki, as it is not an open wiki. So you need permission to be able to make changes. Okay, so let's see here. Who do we got here today? All right, we've got some of the usuals here. Bill Lucas, Duncan Shaw, Hans, Lou is here, Bob. So I just wanted to ask, first of all, is there any topic out there that someone is just dying to talk about this morning? So I'll open the floor up to questions first before I start throwing out some topics of my own. Anyone got a topic they just really want to talk about this morning?
I said already, and I typed the link on the chat box in the group chat on the right side of your screen. I have constructed some pages for the Wiki University. They call it Wikiversity. It's exists already for some time, but they're setting it up now with a lot of effort to produce a complete online university where, in fact, all teachers can participate and all students can participate.
All right, well, I'm sharing your link here. So this is the Wiki University here.
That's just one page of it. It's one of the pages I made.
So you've got your whole thing here, so you can teach.
You can teach your lectures here to other people, and if you are a teacher, you can teach your own students here with online lectures. They made the environment where you can publish your lectures.
Like video lectures?
Well, that's best done on YouTube, I guess. They are mainly just kind of wiki pages, like on Wikipedia. It's the same environment that you work in. Is like Wikipedia.
All right, so I just put in some random quantum physics here to see what some other people have done here. So there's apparently the Wikiversity of Quantum Physics.
Yeah.
So can anybody edit this then still?
Yeah, anybody can edit, but you must obey some rules. You must not make a mass a mess of it. You must work in a professional and official way without disturbing too much people. But you everybody in principle everybody can edit. But what you change can be uh, changed back by the mentors of the pages.
All right. So I'm looking at like things like other physics topics like magnetic fields.
Yeah.
So I've written something here about magnetic fields and reversals. That's a very, very short article.
Yeah, I think they start from the idea that most of the knowledge is already packed in Wikipedia, and if you have some specifics that you want to tell to your students, then you can make your own kind of Wikiversity lecture. So you can do this as a single page, or you can do it as a project. And I tried to start a project called the Hilbert Book Model and make a complete project of that.
All right. Well, here's a basic page on particles.
Yeah.
But they don't mind that you put up your own like theories.
No, you
That's
can
one thing
put
about
up your own theories there. Yeah.
That's the one thing about Wikipedia is that actually you can't publish. One of the rules is that you can't actually write about your own stuff. You can write about someone else's stuff, but you can't actually write about your own stuff.
Yeah, you can also write about your own stuff. I think they let me do there what I want. They let me do the project and publish there it in such a way that it becomes a consumable part of science for young scientists and students.
All right. Well, everybody here, here's some place you can publish your stuff.
There are some rules. You must first look around, and they have introduction pages where you can learn what you can and what you cannot do.
All right. Well, thank you for letting us know about that. That's one thing that us dissident scientists like to do is we like to publish anywhere to anyone who will listen.
I
Who
like to lecture.
don't want to listen?
Good, I switch off.
Because you've got your own web page. Now you have your Wikiversity things. You've actually published books too, right?
I didn't understand. What can you?
I was just saying that you have published your works in all different ways.
Yeah, I used VXtra, I used docs.com, and I have my own website, and I'm now also going to apply Wikiversity.
So, out of all of that, do you think there is a channel which is most effective?
I think in the end it will be Wikiversity
Really?
because
Because that just started.
the Wikiversity exists already for years, but it's not well known.
Uh huh. Well, I usually measure success in terms of whether I know people actually access the source or whether they send me any comments and such.
Yeah, you can discuss content there. There are talk pages. which a kind of chat that you can do within or amongst the people that publish pages. In fact, it is meant to be a university. It's a kind of school, but online school.
If it's meant to be a school, but it still pretty much just looks like wiki pages, I suppose.
Yeah,
That's what before.
they use the whole editing environment of Wikimedia. They use the tools, the same tools that Wikipedia uses.
Yeah, that's why it looks like a wiki.
Yeah.
And this is kind of the problem I have with like MIT say that they like publish all of their classes online, but when you go up there, it's barely an outline of the class. So my criticism of these things is that if you're going to be like a university, then it should be broken up into like this is lecture one, lecture two, lecture three kind of thing. And there
Mhm.
should be some evaluation tests to see whether you actually learned anything. And something like that, something like what you would get if you actually attended a
No,
university class.
they don't have a kind of exams, I guess. There is some hierarchy, and there are search environments where you can type in what you did. You typed in a few terms, and then you reach the papers that treat that subject. So
Yeah,
you
that's
can look
that's my
around.
criticism is that it's still a wiki.
Yeah, it's a wiki.
It should
It's a
be
wiki.
something where I could take to my employer and I said, I took this online Wikiversity course and here's my certificate to show that I passed.
I think that's not the what they want. That's not what they pursue. They just offer it as a publishing environment, I guess.
Yes, in which case you might as well just go publish on Wikipedia, I guess. But the problem with Wikipedia is they don't let you put your own stuff on or whatnot.
No, that's heavily controlled. What you put on Wikipedia is heavily controlled. Here you have much more freedom and can make your own pages and your own project.
Because that sounds a lot like what the John Chappelle uh, Wikipedia is as well. Because once we
Yeah,
give you
you
right
pursue
access, you can put anything
you
you
pursue
want.
the same thing. You pursue the same thing.
Now
But
the
a,
deal with
a lot of very professional people supporting the whole environment, and that's why it probably works quite trustworthy.
now one of the things about the natural philosophy wiki is that it only has limited editing. So I suppose example in Wikiversity, someone could completely change your Hilbert book model pages to whatever they want.
Yeah,
But is that true?
I have not tried both environments yet. I have put some things in the forums, and I have not yet published anything in the John Chappelle wiki yet. I am not able to compare these two environments in a proper way.
Yeah, they're probably very similar, but you'll have to ask for editing rights to
Yeah,
get into the John Chappelle wiki. That's one difference. So that as a dissident scientist, you can go ahead and put up your wiki and not have any fear that someone's going to come over and edit your wiki and like remove things or just change it around completely.
yeah. In the Wikiversity, in principle, everybody can change your work, and you have the ability to change it back.
Yeah, so that would be the difference. If you want to go to a wiki where people cannot change your stuff, then you need to publish in the John Chappelle wiki.
Yeah, I have not found out yet, but there is there is a possibility to archive the work so that nobody can further change it.
Okay. Well, that was very interesting. So, did anyone else have any particular topic they wanted to bring up this morning? No, nobody. Okay. So I'm going to bring out my list of topics. Now, there have been quite a few emails going back and forth about particular topics. So one of those topics is the topic of atomic clocks. So let's talk a little bit about atomic clocks. So the main argument that's going on in the email is how is it an atomic clock works on the Earth as far as do they run the same everywhere? And if not, then what causes these atomic clocks to run at different rates? So first, there's this question about whether atomic clocks should run the same at the equator versus the poles, because at the equator the atomic clock is in motion relative to the one in the pole because it's going around with the Earth's rotation fairly rapidly. So it should have a velocity component compared to the one at the pole. So according to relativity, that means that that atomic clock should run slower.
Franklin, you must be careful with this because you must distinguish between the local clock uh, at the location where it's situated, how it's ticking there, and the clock at some other location that you are observing. There is relativity between the two locations, and as a consequence, you see a different time in the observed clock than the clock itself will feel. The clock itself, all these uh, atomic clocks in universe, as far as they are away, maybe millions of light years away, so also in history, tick with the same frequency. So there is a universal clock that keeps them in sync.
Well, I think there would be quite some controversy with that particular statement. That is kind of the crux of the arguments that's going back in the email. And well, for clocks which are on the planet Earth, I don't think we have that much problems synchronizing those because we can actually physically bring the clocks back together. So I can go take an atomic clock and I can fly it here out of Seattle, and I could put one up in the North Pole, and then I could go put one in the middle of Africa on the equator, leave them there for a year, and then I could go pick those same clocks up and bring them both back to Seattle, and then I could compare the two and see whether one is reading differently than the other. So if one is reading 1 p.m. exactly, and the other one is reading like 1:05 p.m., then we could definitely say that one of the clocks was running slower than the other one. Would you disagree with that statement?
I can only agree with the statement that if you've brought these clocks together on the same place, then they are running at the same rate again, at the same location. If they don't move with respect to each other and they sit in the same location, then these two clocks will again tick in the same rate.
But I can
So
compare them and see
I
whether
don't
that
know.
one
I don't
needs
know.
to be running slower than the
There's an
other.
absolute reading and there's a relative reading, and the absolute reading, that's what I'm not speaking about. The relative reading will be the same. It ticks with the same frequency. When it has traveled around a lot and then comes back, it will come back and again tick at the same frequency.
Okay, well, let's move on. So, suppose we have these clocks, they're at the equator and they're at the pole. But this has actually been done, and they find that the atomic clocks run exactly the same rate whether they've been at the equator or at the poles. So the question is, how could that be? Because the clock at the equator ought to be running slower because it is at a higher velocity. Now, the answer from the mainstream is that because the Earth rotates, the world, because due to centrifugal force, actually gets a little bit egg shaped. It gets flattened on the top and the bottom, and it gets a little bit wider at the edges. It's like if you took like a water balloon and you spun it around, it would get wider in the middle there. So what they're saying is that elevates the clock at the equator by about 23 miles. So the clock at the equator is 23 miles higher than the clock at the pole. Now, as you get higher, that slows the clock down because it has because in addition to velocity, gravity also affects an atomic clock. So as the clock climbs out of Earth's gravitational field, it begins to run faster. So it's an opposite effect. And they're saying that by sheer coincidence, that the reduction in the gravity field exactly cancels the decrease in speed of the atomic clock because of the velocity. And this is why all clocks at sea level tick at exactly the same rate, right? Now, there's some other people who believe that the Earth actually isn't spinning. There's people who still believe that the Earth is, in fact, the center of the universe. And their arguments are that if you look at the Earth, it still looks like a perfect sphere. And that the reason why clocks tick at exactly the same rate all over the Earth is because the Earth isn't moving. So they're saying that the equator actually is not moving relative to the poles. So that is one controversial solution to this problem. So the real question is, how do we know that the atomic clock is actually 23 miles higher, or that is the Earth really egg-shaped to that tune? I mean, 23 miles out of 3,000 or 6,000 miles, the radius of the Earth is like hardly anything. That's not anything you could optically see from pictures in space, for example. So that's one possibility, but it is kind of a coincidence that the gravity and the velocity would have to exactly cancel everywhere in the Earth, since apparently this has been empirically measured, that atomic clocks, no matter where you put them on the Earth, all tick at the same rate. Or it could be something like Hans says, is that, I don't know, there's a global clock and that all these things tick at the same rate. But that is one of the controversies. I mean, does the gravity cancel the velocity at the equator? And one of the questions that got brought up, I see on the internet, is that why is it the gravity is less at the equator versus on the poles, because you'd think that there's actually more mass underneath the clock where we're, because it's sitting on bulge, than it would be on the poles. And the answer is just simply that the clock is, they're measuring it basically from the center of the Earth. So your gravity depends on how far away you are from the center of the Earth, and not so much how much mass is directly sitting underneath you. Because one of the weird things about gravity is that the gravity that, like, I'm feeling right now sitting here in my seat is not due to just the mass that's sitting underneath my feet. It's actually the cumulative force from every single bit of mass on the planet Earth, even from China, is contributing to the force that I'm feeling. And you would think that that would be a really, really hard force to calculate. That there's gravity coming from the wall behind me, there's gravity coming from the ground beneath me, there's gravity coming from the building next to me, and there's gravity coming from Mount Rainier, which is 50 miles away from here. How do you calculate how that acts? Now, I believe Newton did this, and he, like, through the magic of calculus, figured out that all of your gravitational force acts as if it were concentrated in a point in the center of the Earth. So for anything which is roughly spherical, you can calculate the force of gravity as if there was no mass except for some baseball-sized thing in the center of the Earth. So if you think of it that way, then it doesn't matter that there's, it looks like there's physically more mass underneath your feet. All that really matters is your distance away from the center of the Earth. So, for example, even if I took my atomic clock to Mount Everest, you'd think that all the mass of Mount Everest might actually make your gravity higher, but it doesn't. Actually, your gravity will be lower even at the top of Mount Everest, even though you're sitting on this mountain of material, because that mountain of material is like nothing. It's like a dust speck compared to the entire mass of the entire Earth underneath your feet. So it only matters your distance away. So if you are 23 miles higher than you are at the poles, then that will decrease your gravity by that much. So do you guys understand those principles?
Yeah, but
Or
I
have
don't
a
think
problem with them?
experiments confirm any of that. Do you have any experiments that confirm that claim?
The gravitational claim. Now, I don't in
Well,
particular.
what I know for a fact is that people who want to know what the gravity is at a particular place on the surface of the Earth they measure it. They don't calculate it; they measure it. Why
Yes,
would
they
they measure
measure
it
it.
if a calculation is good enough?
I mean, definitely you can see a decrease in gravity with height. I mean, they have these gravity meters now, which are so sensitive, they can detect a difference of about 10 centimeters height difference. They're that sensitive.
Right. Well, what I'm saying is that if you're doing an experiment, you know what the force of gravity is at a particular point, you measure it. You don't calculate it. You get out one of these gravity meters and measure it because apparently, you need to measure it accurately enough to know what it is.
Yeah, well, I would like to see some data on this myself. So I would like to see a gravity meter stuck on the equator and a gravity meter stuck at the poles, and show me that the gravity at the equator is less than at the poles. That's a fair thing. So I presume that must have been done, but I have no idea whether it has been done. That's what mainstream would tell us, that the gravity at the poles is less, I mean, it is more than at the equator. I believe I've seen several web references to that. So
Well,
it's
that's a good
probably,
point. I mean, I would think you could go on the internet and do some searches and see whether or not there are any measurements of that. I certainly don't know the answer.
Yeah, hello. This is Bob.
A couple of points. There's a there's a laboratory in England, National Physical Laboratory, uh, where I obtained an empirical equation for gravity that people use, especially people who are searching for oil and underground things. It's an empirical equation that has two parameters, latitude and altitude. And I have a copy of that equation that I have, and at some point intended to use that to compare to measurements and other calculations. Secondly, I also saw on the internet one time there was a map of the Earth, and it looked like a prune because it described the gravitational force around the Earth, and theoretically it looks like all points. I doubt that it's all points, but a significant number of points around the Earth where uh, the gravitational measurement was, and you can see that the whole thing is just totally rippled all over the place. But at the same time, and I don't remember this, any of the detail of that, that there should have been a measurement then at the equator and at the poles. Just making comments. It's been a long time since I looked at some of that, so I just thought I'd throw that in there. Uh, so there is an equation describing the force of an empirical equation after many measurements. This is what the National Physical Laboratory did. And it's used to help guide exploration. End of comment.
Let's see here. I think I. Let's see here. No, that's not it. I think I found that map of the Earth here. Let's see if I can get that up here. If I can get my menus out of the way. For some reason, I can't see that. Oh well, if I just share my screen. Okay, so that apparently is a gravitational map of the Earth. So not exactly 100% spherical. Kind of lopsided. So basically round, but not a perfect sphere.
This is Bill Lucas. I have a grandfather clock, and if you've had one, you know that the length of the pendulum is adjustable. And that's because over time, the gravitational field at any point on the Earth is changing. That's due to the expansion of the Earth. The Earth doesn't have any more mass to speak of, but it is expanding in size. So that causes the gravitational field to change, and when you're getting further away from the center, of course, and but anyway, that's an interesting thought that people who do clocks have discovered that they have to take that into account.
Now, grandfather clocks are very dependent upon the pendulum length changing. For example, they're very vulnerable to temperature changes because as things heat up, the pendulum gets longer, and then it causes the clock to run slower in warmer weather versus when it's put in a colder environment, the pendulum shrinks up and it will run faster. And so this is why the pendulums in these grandfather clocks are actually made out of various combinations of things so that they try and compensate for that. So so that the length change is reduced as much as possible. Now, this is kind of a topic in time because it's an example of what some people might call time dilation. So if I take a grandfather clock and I stick it in Africa, it runs slower than if I stuck it in the North Pole. But now the question is that time dilation, the way that people talk about that with like these atomic clocks, that time has been changed? But I would argue that it's none of the sort. The only thing that's happening is that it's just changing the rate of the mechanical clock. It's not changing the rate at which time progresses in the universe, which I think is an important point. That it's quite clear in the grandfather clock and the changing length pendulum that you're not actually changing anything about the rate at which time flows. The only thing you're doing is you're changing how that clock works. So the only thing you're dilating is that clock, not time itself. I see, Mitch, you have a flag, you have a comment?
Yeah, thanks. Coming back to the point of the compensation of the difference in gravity or elevation, couldn't they do the experiment raising one of the atomic clocks up on top of a mountain so that the G-force is the same um, for the one at the equator and the one at the pole, and then compare them? You would think they'd be able to compensate for that difference in elevation or gravity somehow before they do, and then do the comparisons. I was just kind of wondering if they did anything like, or if they thought of doing anything like that.
I don't know. It's probably something you could search on the internet to see whether anyone has like taken either a gravity meter or a atomic clock or both and taken them up to a mountain. Although the sensitivity of our gravimeters is such as that you wouldn't have to really do that. You could go to a high building and you could detect the differences. And I've tried to do experiments where I just take the simple accelerometer that's in my tablet, because all tablets these days have these actually fairly sophisticated sensors that will directly read out the value of G on your tablet. So I took that and I stuck it at the bottom floor of my building, and I read what the value of G was. And then I took the elevator up to the 24th floor, and then I measured what the value of G was there just to see whether I could see any appreciable difference. Now, the problem with the value of G being read out by these accelerometers is that it varies quite rapidly. So it stays about 9.6, but the lower digits are just jumping all over the place. So it's kind of hard to see, within the precision of the device, whether you've got a decrease in gravity or not over that short a distance. But it kind of looked like there was generally a decrease in the value of G when I was on the 24th floor versus the first floor. So we do have some pretty good instruments, but these are all ideas for experiments that you can suggest or to look for. Probably people have done stuff like that.
Yeah,
Okay, so
oh,
Roderick Berry has a comment. What would you like to say? Let's see here. We can't hear you. Do you have your microphone on? I think we have your microphone off.
How's that?
There you go. That's better.
Can you hear me?
We can hear you now.
I'm new. This is my first meeting. This is interesting.
Well, welcome.
2 points. Thank you. One is you had mentioned a water balloon earlier spinning. It seems to me, in an intuitive sense, that it's plausible that the forces that cause the water balloon spinning to bulge at the center versus the poles could perfectly counteract any time dilation expectations based off of gravity and velocity at the equator versus the poles And my point is, if because the Earth has been spinning for so long, and it used to be, it started out molten. The fact that it is not a perfect sphere, to me, it makes sense that there is a plausible explanation for it. And my uh, my expectation would be that if you took a solid sphere, a rock, and spun it, you would get different time dilation at the equator versus the pole. Does that make sense?
Yeah, that's the expectation that if you took any sphere and you spun it and you put a clock on the equator, that it should run slower. But the funny thing about Earth is that I believe they've done this and they found that no, it runs exactly the same no matter where you put it.
But that's only true on the surface of the sphere. And my point is, I'm I'm submitting that is true because the Earth is old enough, and it was molten at one point. It's old enough such that it reaches this equilibrium exactly like a water balloon would, which is fluid, and it doesn't retain its shape. I'm saying that if you took an actual sphere of solid form that retained its shape and spun it, you would get differences between the equator and the poles.
Yep, that is the expectation. But what I find a little bit hard to believe is that the amount of spinning and the amount of non-sphericalness would exactly cancel on the surface of the Earth. It just seems like a huge coincidence that it does that. It's kind of like when we have solar eclipses. Well, there's a solar eclipse coming up in the next couple of months here on the West Coast, and I'm definitely going to go and see it. That the size of the moon exactly, and I mean exactly, covers up the disk of the sun. I mean, that's just like, is that like just a huge coincidence or what, right? So it just seems like this canceling of the velocity by the gravitate by the bulge of the Earth also seems to be one of these fantastic coincidences. Because I think you could easily see that it might not be that way. I don't think maybe someone has figured out the equations to this, but I don't think that those two have to be equal under all conditions. I don't know why that would be. Because it could easily be that the Earth spins out more, and that equatorial bulge is such that it doesn't cancel that way, but that it perfectly cancels across all the surface of the Earth. Seems like a gigantic coincidence.
Is your name Franklin?
Yes, uh-huh.
Is the sentiment in this forum, is the sentiment that time dilation doesn't exist, or what is it that we're discussing?
Well, I'm just it can be any. We don't have any particular sentiment except for what the speaker represents.
Okay.
So
okay. So there's different. There's different views.
Something different, and that's why I'm trying to elucidate. What people think is time dilation real? I just argued that time dilation isn't real. The only thing that really changes in these experiments is the rate at which the clock ticks, which is a lot easier to see in, say, a grandfather clock than an atomic clock. But it's fundamentally the same thing. Now, one of the things I was trying to argue in the emails is that I think that the atomic clock works pretty much the same as the grandfather clock, because inside the atomic clock fundamentally is a quartz crystal oscillator. So that's a physical crystal. You can think of it like a tuning fork that's just vibrating back and forth. And that's a quartz resonator, and that's what we have in our digital watches, and that's pretty good. Except it's not terribly stable. Our digital watches will lose a second, 1 second every month, and that's not very good. So the inventor of the quartz crystal oscillator thought of, well, let's lock this quartz crystal onto something which is more stable. and then we can make our clock much more accurate. 1 second over like 10,000 years is the desire. So what they did is that they found that the atomic transition of a sesamium atom is very constant. That the amount of energy it takes to excite an electron to go from one level to another remains the same under almost all conditions. So no matter what the temperature was, no matter what the fields are, the amount of energy it takes to cause that transition is very, very constant. So, just like if you excited any atom, it emits a spectra like helium, like hydrogen, you've probably seen, emits very specific spectra. This is kind of the same thing, but the reverse is also true, is that if you inject energy into an atom, it will cause a transition, and you can measure that amount of energy very precisely by frequency. So there's a relationship between energy and frequency. Energy equals Planck's constant times frequency. So what they do is that they inject this, it's basically microwave signal. This is like about 9 gigahertz onto the sesamium atom. And if they tune it just right so that they are providing exactly that amount of energy to do the transition, it will cause the atom to take this different state. And then they can take and they can separate out and count how many of those atoms actually got into that new state. And they basically adjust the frequency until they see the maximum number of these atoms changing over. So that means that this frequency is exactly at the energy needed to maximize this transition. So the question is, how on earth do you build a clock out of that? But I think one of my points is that people think that sesamium atomic clocks work by counting like the 9 gigahertz signal. And I believe that is fundamentally not true. There's nothing in an atomic clock that's really being counted at 9 gigahertz, because I told you before, at the heart of an atomic clock is actually a quartz crystal resonator, not any different than what's in your watch. But what they do is that they take this signal from the quartz crystal, which is about like 10 megahertz, and they multiply it to get to like 9 gigahertz. And they use that as a signal that's going into this thing that's shooting microwaves at the sesamium atoms. And what they're doing is that produces a voltage, which represents, how accurately you've hit that frequency. And that's feeding back into the quartz crystal to tell it to either slow down or speed up. So that if the quartz crystal slows down, what happens is that reduces the frequency going into the sesamium atoms. And then what that will do is that will reduce the number of sesamium atoms being detected at the maximum, which reduces the voltage coming out of the atomic part, which will then go into the feedback loop, which will cause the quartz crystal to speed up. Because basically, the way quartz crystal works is that you got to hit it. I mean, I saw a video where basically some guy was just like tapping a bit of jello. Once you hit it, then it vibrates at a resonant frequency, but it will stop. So you have to keep on hitting it. And the frequency at which it will actually ring at kind of depends on how often you hit it. And so with this feedback loop, this is causing that quartz crystal to speed up or slow down so that it is more stable. So it's basically locked to this energy transition that's happening in the Sesmian atom. But basically, we're really not doing anything. We're really not counting like the signal that we are hitting the Sesmian atom with, which is like the 9 gigahertz signal. We're not counting the 9 gigahertz signal. We're still only counting basically the 10 megahertz signal coming out of the crystal oscillator. And the crystal oscillator, like I said, is just like the pendulum in the grandfather clock, which is swinging back and forth physically. And but my argument was that people think that we are counting the 9 gigahertz signal, that we are locked to the atomic process. But I'm trying to tell people that no, we are still depending upon that quartz crystal to give us the actual time signal. And I'm saying that it's possible that, like Hans said, that the atomic part actually is completely immune to these relativistic and gravity effects, that thing is actually the same, the same frequency or energy. Actually, we shouldn't really call it a frequency because it's really an amount of energy which is the same no matter what. And that the atomic part is just providing the locking mechanism so that this crude quartz crystal doesn't drift all over the place. But it is the quartz crystal which is vulnerable to environmental effects such as velocity and gravity. So my own pet theory is why is it an atomic clock runs slower in a large gravitational field? Is for the same reason that gravity basically concentrates all matter next to it. So like in the atmosphere is much thicker here down on the surface than it is out 10,000 feet up, and there is a constant decrease in that density as you go up. Same thing with the oceans. You go to the bottom of the oceans, it's much denser than at the top of the ocean. Now, my own pet theories say that there is something that's unseen, which is the ether, which is a positron-electron sea, which we generally don't currently recognize, but it exists as a matter sea, which is compressed by gravity, just like the atmosphere. Now you've got these quartz crystals which are running in this medium, and as it gets denser, that changes the resonant frequency. So as it gets denser, it gets harder to push through that stuff. So that decreases the speed at which any clock will tick on the Earth. So that is my assertion about why gravity causes clocks to run slower. It's literally like slowing down some mechanism, like me trying to drag a spoon through molasses. It's going to take longer to do and much harder to do than if you're dragging a spoon through, say, water. So this is how you can think of, why, if you're wondering, how do I remember that gravity slows clocks down? You can just remember that gravity makes things thicker, just makes things slower. But once again, that is my own personal opinion on how this works.
Does your pet theory address velocity, time dilation through movement?
Yeah, that would also be effectively a density effect, because if you're thinking that it's a matter of how many particles you have to move past. So you'd have a fixed point A and B. So if there's like no velocity, then there's only like, let's say, 1 million particles between my two hands here. But now if I start blowing wind through there, then there's going to be like more particles, because you've got particles that are going by. It's going to be, I will actually have to transverse like maybe 2 million particles to go from point A to point B when you're in a moving situation. So, and that's why you have to figure out all this Pythagorean stuff, because at that point you're when anything going from point A to point B is actually going to have to take basically a diagonal path when it tries to go through that way.
Right.
So I would explain it that way. I would explain that actually all actions happen actually at the speed of light between individual particles. But the denser the material you have between you, that will slow things down. So like we see this easily in like refraction effects. So light travels slower between in glass than say air. And I would claim that that is due to the fact there are actually more particles that it has to transverse in the glass versus the air. And I think that if you were actually able to operate a clock inside of solid glass, which you cannot, but you would also find out that if you could, that the clock would run slower inside the glass than it would in the air. So maybe someday we'll be able to build a clock that can run in solid materials, and then maybe we could actually see that. Like I'm thinking maybe you could just build a clock by building two mirrors in a block of glass and then using that speed that the light bounces between those two mirrors as the clock, and you could see that any clock built that way will run slower inside the glass than in the air. I think we already know that's true because we know that the speed of light in glass is slower.
Franklin,
Yes.
this is Bill Lucas. We've never pointed this out as far as I know, but the atomic clocks and the theory of relativity, both special and general relativity, are known to be only approximations. And the reason for that is from electrodynamics, we know that, and if you work with accelerators, you learn this very quickly. You learn that electrodynamics is controlled by radial terms, velocity terms, acceleration terms, and dAdt, which is radiation reaction terms. And special relativity doesn't take into account the acceleration, the emission and absorption of radiation, and all matter is continually emitting and absorbing radiation, and it also is recoiling from that. And none of that is taken into account in special relativity. Even general relativity, which has some acceleration effects, does not take into account emission, absorption of radiation, and radiation reaction. So because of that, these theories are known to just be approximations. And if you want to know what the proper way is, well, I published that in my book on the universal force. But anyway, that is what we know. I mean, the scientific community, the politically correct community, they know this. They just don't emphasize it.
Yeah, there are always other effects other than gravity and velocity that are always present in all of these systems. I guess most of us don't have to worry about that unless they're actually building a synchrotron, in which case it makes a big difference. So you have to know these things precisely.
Right.
But
well, those are extreme
for
cases.
discussion purposes, you know, the gamma factor, all that kind of stuff, it kind of works. Although I've personally never seen it, so. But I was just wondering, did anybody have any comments about what I have to say about how atomic works or how atomic clocks work or how they potentially could work? So, you know, I have my own pet theories about, you know, how that all works. But there's still quite a bit of controversy as to what an atomic clock is actually ticking at. You know, is it really ticking
there's any
at?
controversy, Franklin? What makes you think there's controversy? I mean,
Well, I'm
I don't
talking
see any
with,
controversy. Where is there controversy, Franklin?
well, I'm talking with on the emails with Ron Hatch, and of course he vehemently denies that, you know, the quartz crystal has anything to do with the time base.
Well,
I mean, most people think that an
the
atomic clock is locked on the atomic process.
I'm not really sure I understand what your point is. The point is that what you have is a feedback loop. Okay, we talked about this before. I don't think and what is meant by feedback loop. That's my conclusion from what you have said. You don't really understand the concept of feedback and feedback loop. And what is happening in the clock is that the quartz crystal frequency is adjusted by a tuning mechanism so that it is locked to the frequency of the cesium atom transition. Okay. And that is what the principle of the clock is.
Yes, that's absolutely correct. Now, my only question is if my only question is, and I don't know if it's true or false, is that if the cesium part of that clock was invariant under different gravity conditions. So, for example, I can measure the difference in an atomic clock rate versus the ground floor versus the 100th floor of some building. You can do that. Now, my question is, if the cesium part of the clock remained invariant under those conditions, that you would basically still see the quartz part of it slowing down, but because the cesium part, we're not counting that part. We're counting what's the number of beats in the quartz. That because I believe that if you actually built a clock which really looked at the actual cesium transition, that you would come up with a truly atomic clock. And I think they're trying to build something like that, where they get rid of the quartz crystal out of that thing. You would find that
what they're doing is they have what's called the fountain
effects.
clock, and I forget the name of they have what's called the cesium fountain, I think. And the idea is that the gravity effect is removed by the procedure. But I don't really know that much about it to really comment on it. But it would seem to me from what you've said, I mean, what the facts that are known are that when they take a clock that's calibrated at ground level and they take that clock and they move it up to put it in an airplane and fly it up very high, it changes its frequency of the cesium atom transition because the clock changes the time rate at which it measures time. So that would imply that the cesium atom transition is being changed by the gravitational potential, which
Now, see, that is exactly what I'm questioning: is whether the cesium atom energy actually changes or not. Because I'm saying that.
Well, what we're saying, I mean, essentially, these are the empirical facts. I mean, that's the facts. Now, the other question is whether or not this is consistent with with general relativity. And it seems if you read general relativity books, it seems like that's not exactly what general relativity says should happen. And that's kind of confusing. So, this seems to be one of those examples of you have a theory that sort of suggests an empirical fact. Then they do this experiment and they have an empirical fact. So they say the theory is confirmed by the experiment, but it seems that the interpretation of the theory isn't exactly what the theory actually says. Do you follow what I just said?
Yeah, experiments are always subject to interpretation. So, for example,
well, what I just said was that if you read a book on general relativity, it's not exactly clear that the general relativity predicts the experimental outcome as was described, as I just described it, which is you take a clock at sea level and you bring it up to a high altitude and then it runs at a different rate. That's not exactly what general relativity says is happening. that part's kind of confusing because it's not exactly clear to me. When I read this in these books, it's kind of like, I really have a hard time understanding what exactly is happening because they're trying to make the theory look like it fits into the experiments, and it's confusing.
What's the
It's
description?
it's terribly confusing, Harry. It's totally confusing.
Well, but so what is your claim? Your claim, I mean, the fact is that when a clock that's calibrated at sea level is raised or taken up to a higher level relative to the surface of the Earth, the experiments are fairly, I mean, they all are pretty clear, and the errors in the experiments are relatively low relative to what is measured as a change. So it seems that if you take a clock and you raise it up high, it will change its frequency and run faster, as I understand it.
Okay,
Correct?
my oddball claim that nobody likes is that I claim that the cesium atom transition doesn't change at all with height. So do you understand that? That the cesium part of the atomic clock doesn't speed up or slow down at all. All it's doing is remaining constant. And that what's slowing down in the atomic clock is the quartz crystal.
In a
That's my
universal,
claim.
are you claiming universal constant time?
And yes, in fact, I am
Okay,
claiming
so
universal
Newtonian time.
constant time.
Okay.
Because that's another part of my pet theory, which is that time is actually quantized. That and that like in a hydrogen atom, for the electron to transition from like shell 1 to shell 2, that will actually turn out to be an absolute universal constant. That the rate at which that transition actually occurs is 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 at actually all changes in the universe. They all actually happen at to be running slower than the speed of light are simply because it's got more particles to go through in order to register a change. And in that way, there is going to be like a master universal clock. And I have a paper called the God Computer, which is basically asserting that the only way that everything can be in lock sync to each other is if there's like this master CPU clock in the universe that everything is running at. So just like in your desktop computer, the ones and zeros can only change at that rate.
So you have
everything
your pet theory,
actually locked.
Franklin. Your pet theory is basically like an ether theory where there's a substance, and as you move through this substance, it slows down clocks, whatever their form, right? But that's fine. But I have a problem when we question general relativity and special relativity because mathematically they've been validated through GPS satellites. I mean, they have to account for both special relativity and general relativity's effects in order for our GPS satellites to stay synchronized.
Yeah, but
So,
Yes, I
doesn't
have no
take
problem
away.
with that.
That
I'm sorry?
doesn't.
You
Sorry.
totally have to meet the empirical measurements.
Say it again. I'm sorry.
I think that Franklin is right about that basic physical processes are running all in the same cycle. So there is a basic universe-wide clock that keeps everything in sync. The problem is with relativity that you are not connected to that clock with your arms or anything. You get your information that's transferred through a continuum. And that continuum, the transfer through the continuum, uh, does what the Lorentz transform describes. It changes the format of your information. what you observe is not how the clock ticks. It is
Yeah, I would assert
the information that
that
is
all
gained
physical clocks that
by
you
the
can make.
transfer of the continuum that brings you the information. You are not directly connected to that clock. You have to look at it. And if you are moving with respect to each other, then that information transfer is affected. And how it is affected is exactly described by the Lorentz transform.
Yeah, I would argue that the quartz crystal, I mean, that's something that's made out of billions of atoms. I mean, it's macroscopically, you can see it with a microscope. That thing is waving in space with its billions of atoms, right? It's not an atomic process. So my assertion would be that if you built an atomic clock that did not contain a quartz crystal oscillator in it, that you actually measured the speed of actual electron transitions, that you would have an atomic clock which would in fact be immune to these gravitational and velocity effects. But you have to build it at the atomic level, not at quartz crystal or
Have you guys
pendulum.
heard of Franklin? Have you researched optical clocks? Those are fairly new, and they're supposed to be many orders of magnitude more accurate than atomic clocks. And I don't know the internals of how they work, but they are supposed to be the most to date the most accurate theoretical clocks that that man can build. It might be something that you guys would find interesting.
Yeah, I've been looking at that. I'm not. When I looked at the references, it didn't quite sound like they'd actually created one yet. But my prediction would
Yeah,
be that when
there are two schools that have one. They're both they house them in a van basically, and that allows them to move them around. It's basically like a mini lab on wheels. I'll post some links to the group chat here. Give me a second.
okay, sure, I'd like to see whether they got rid of the quartz crystal in even that one, because I believe when I read it, the principle is still basically the same, except they're using light frequencies, which is even higher than the 9 gigahertz microwave frequencies of the cesium atom, but that would still be locking onto a quartz crystal. And I'm saying that with an atomic clock, that is the element which is vulnerable to time dilation. And that the bigger claim that I'm making is that there is a universal clock which is invulnerable to any time dilation, and it ticks at a constant rate across the entire universe. And that if you could build a clock, and this clock would have to run something at the rate of 10 to the 20th hertz, because that is the rate at which it's basically, you know, Planck time over Planck distance kind of thing. And that's like horribly fast. I don't think we have any equipment that could measure anything that's running at that rate. But if we did, we would find a clock that didn't matter whether you took it from the mountains, took it into space, you would put it anywhere, you would find that that clock ticks at exactly the same rate everywhere. And that relativistic
Why would
effects.
that be? Why would that be, Franklin? I mean, I see no particular reason why that claim would be true.
Well, of course, there's no particular reason. That's why I'm claiming it. That's my wild claim.
And what is your
I mean,
wild claim?
actually, in order for my theories to work, that has to actually be true.
Your claim is, if your claim basically boils down to, as I understand it, that if I have no physical effects on my ideal universe clock, any place in the universe that I place my ideal universe clock, it will always tick at the same rate. Now, that's a bit of a problem because you actually need to have two clocks because you can't really tell whether there's a change. You have to have something standard clock someplace to measure it against. So you have to have two clocks. So you have a clock that you're going to call your standard clock, your standard universe clock, and you're going to have a copy of that standard universe clock, and you're going to move it around. And your claim is there's no difference between the two, right?
Well, the claim is that everything, all the ticks happen at exactly the same time. So if you have an electron and it is vibrating and it's sending a wave to from Earth to Alpha Centauri, that when it interacts with the proton or something, which is also ticking, but in the opposite phase, that when the phase from the electron from the Earth reaches Alpha Centauri, because the clock ticks happen at exactly the same time, they will be exactly 180 degrees out of phase.
Franklin, you have problems with redshift.
Electron in the universe.
Franklin, you have problems with redshift. Colors that come from far galaxies are shifted to the red color in the direction of red when they arrive here. So something is happening in between. But atoms that are in that distant galaxy have the same signature with respect of the spectra as the atoms here. Only the when the signature is coming here, it's red shifted. That's the Hubble law.
Well, my question is that if the velocity does affect atomic processes, then that would mean that not only would it be redshifted, but it should actually be even lower, right? It should be, in addition to the redshift, there should be another shift. So like it would, if you're changing the energy of the cesium transition, or if you're changing the energy at which the hydrogen atom emits spectra, I mean, the relative spectra might be the same, but if you were to actually slow that down or change the energy, then the whole spectra should actually be shifted. Then how could you, then that is something I would be looking for, is that is some evidence that the spectra is sensitive to the time or even gravity. I guess this is something you could do down on Earth. You could look at the spectra of hydrogen, and there should be some difference whether I'm looking at the spectra on the bottom floor of my building, and then when I take it to 100 stories up, where gravity is less and time is running faster, I should actually see a different color up in the top. But do I see a different color, or do I see exactly the same color? I don't know what the results of that are, but that is my question. So if there is no universal clock, then one would predict that if I took my spectra and I took it up to 100 floors up, that it would be different than on the ground floor where the gravity is stronger.
Franklin, here's the problem. How do you know whether time changed or whether something physical in the clock changed? You're claiming that time doesn't change.
Look at the spectra. If you look at the spectra of hydrogen, so there we've eliminated the time component. We can have a very sensitive silicon detector.
Let's back up. Let's back up. The assumption in physics, as I understand it, now that maybe you want to argue about this, the assumption in physics, as I understand it, is the laws of physics regarding atomic transitions are the same everywhere, irregardless of where I am, and that it's time that changes. And are you disputing that assumption or not?
I'm saying that if you actually built a clock that depends on the actual transition itself, that would also be immune to gravitational and velocity effects.
Because your claim would be that it's a law of physics that the transition of an atom is always the same, irrespective of where it is.
Well, it may or may not be. I mean, we need to have some experiments to either confirm or deny that.
Well, basically, my position would be, or my argument would be, that the assumption that physicists are making is that the transition of the cesium atoms is not affected by it's a constant, and so the assumption is it's an invariant and doesn't change with gravity or velocity. And so any difference in the clock that you measure would be due to a difference in time.
Okay, what about the Rydberg constant? It looks like it depends on C.
What about the Rydberg constant?
Well, that's what defines the frequency of a transition.
Yeah, I don't know if you're that would be outside of.
I just looked it up on Wiki.
So, I mean, I don't understand your point.
That if it's
I mean, the fact that Rydberg constant is a constant implies to me that it's an invariant and doesn't change.
Well, but
I think your question is: Are you saying? Are you questioning the Rydberg constant? Are you saying the Rydberg constant is not a constant?
Well, it depends on C. According to Wiki, it looks like.
How a constant can depend on C.
I'll look it up.
Well, the speed of light is supposed to be, I don't know, constant in, say, a vacuum.
It's a proportionality, essentially a proportionality constant, just like.
But otherwise, generally speaking,
my point is that if the speed of light is changing because of the density of the ether, which depends on the potential local gravitational potential, that could explain the difference in clock bias.
Well, that would then mean that the assumption of physics that the laws of quantum mechanics in atoms depends on where the atom is located and is not independent of its environment, right?
Maybe.
Well, my argument that was going out the email is that the people were arguing that transition actually does change. That's a contradiction to what that.
If you're saying that the energy in the transition or that the frequency of the transition is not a constant irrespective of its environment, of the physical environment of the atom, then you have to say that it's time that's changing. That seems to be the logic that's being employed. If you say that the physical environment can change the transition of the atom, then you have, I think, a physics that's different from the current physics that we have. Now, I could be wrong about that, but that's my conclusion about that.
Yeah, I mean, there's two possible conclusions. That like people like Vijay and Ron are presuming that the frequency of the cesium atom actually slows down or speeds up in the gravitational field. That they think that they're measuring that 9 gigahertz signal, and that increases or decreases.
Okay, so now the question is that what general relativity or the currently accepted mainstream physics community would agree with? That's my question.
I don't think so. I think what you said about the cesium atom transition not changing under any conditions would probably be closer to the mainstream view.
Okay, so there you have basically a difference of in claims. Is that what you would be asserting, as I understand your position? Your position is that the time is not changing at all, and so any difference in clocks that we measure are due to changes in the environment of the clocks.
Well, I'm claiming that the atomic clock is just like the pendulum clock, and that time isn't actually slowing down. It's just some physical mechanism within the atomic clock is what's slowing down.
Franklin, what
Time does not change.
what about radiation rates? Is that a purely atomic phenomenon to you? Like what I'm saying is there can't be a difference between a pendulum clock, a physical process, a macro scale physical process, and a micro scale atomic process. No, I'm not saying there can't be. I'm saying I don't believe there is a difference. And if there were, then we could actually tease apart that time rate passage difference by things like the rate of radioactive decay or some other thing. I don't know. I mean, it from all evidence gathered so far, when we claim that time has slowed due to gravity or time has slowed due to um, relative velocity, all processes slow down. Everything does. Our instruments, our perception. It's not just some physical pendulum swinging on the wall.
No, I would disagree with that. I would say that if you were to stick with my pet theory that there is a constant background universal click, you'd find that every single other clock you could build out of is some integer quantum number of those clicks. And then when things slow down, you've just increased the number of quantum clicks that it takes for that clock to tick tock.
Okay, so you're saying even atomic processes like radioactive decay rates, they might slow down as predicted by relativity, but they are just taking longer relative to this mysterious universal clock.
Yes, they would just be taking longer to this mysterious,
Got
like muon decay. I mean, you would have to figure out what muon decay is, and if it's physically something going from point A to point B, anything traveling distances are going to be vulnerable to velocity effects. So so a muon would take, instead of like 1,000 clicks of the universal clock, when it's speeding down at near speed of light, it might take 1,000,000.
I got it. I got it.
But that universal clock is still ticking in the background, and everything else should be measured in respect to that.
Does your pet theory account for the relativity of motion? So like you got two muons traveling relative to each other, something close to the speed of light. Wouldn't your theory predict that one of them was not moving relative to the ether and the other one was, therefore they would not exhibit the same behavior?
Well, if they were moving in different kinds of ether, they would. But if they were just going side by side within the same ether environment, then they would.
Let's say traveling towards each other. One is not moving relative to the ether, but the other one is. And there's a third party who is standing between them or sitting between them or observing them, claiming that they're both moving the same speed but in different directions. It just seems like the idea of an ether gives an absolute place in space and time that is broken by relativity. By relativity meaning if you're moving and if you and I are moving relative to each other, we both make the same claims about the other person regarding the rate of their clock moving.
Well, that's the handy thing about having a physical ether, because all of those questions go away. Because if you have a physical ether, then you can assign absolute velocity to that physical ether. So like if you have air or a body of water, you can assign absolute velocity relative to those things. So if I had a muon and it was sitting in my swimming pool and that was stationary to that swimming pool, and I had another muon that was moving relative to that swimming pool, then I can assign absolute velocity. One of them is 0, the other one is 1,000 miles per hour. And we would predict that the one that's staying still will expire faster than the one that's moving 1,000 miles per hour. So I think having a physical ether basically gets rid of all of those nasty relativity questions, since you can't assign absolute velocity. But now the trick is that it's all relative to your local ether. So, for example, there's some theories that say that the Earth itself entrains a local ether. So, sitting here, right here in my room, the relative ether velocity is like 0. But outside of Earth's gravitational field, where we're not entraining uh, ether particles, that you should say that I should be moving at 30 kilometers per hour. It's like if I'm in my car and I'm moving at 70 miles per hour and I put out a little wind meter, it doesn't read 70, it reads 0, right? Even though I'm moving at 70, right? So the ether itself, as a material substance, can be moving at different rates in different places in the universe. So this is another reason why we don't say measure. It's hard to measure the motion of the ether on the Earth because we don't see the orbital component. But we do see things like the Signac effect. We can see the rotational component of the Earth through the ether, which would tend to indicate that we are sitting in an entrained ether bubble. Or there are some people like the center, think the Earth is the center of the universe, think that the reason why we don't measure that is because Earth isn't moving at all. So if I stuck the Morley experiment on the moon,
wait, does anyone in this forum think that?
Huh?
Do folks in this forum think that the Earth isn't spinning?
Oh, we have some people on the CNPS who vehemently believe that the Earth is in fact the unmoving center of the universe, and that everything in fact moves around the universe. You look at like Robson Jonas. He's very active in our emails right now, asserting as much as possible.
But there's a problem with that, in that from the mechanical point of view, there's no difference between whether the Earth is at rest or is it spinning. I mean, this is
that's not true.
Wait a minute. That's the principle of relativity.
Okay, but hold on. Spinning.
That's the principle of relativity, is it not?
No, that's not true. Motion, linear motion, yes, that's the principle of relativity. I can't say if you're moving or I'm moving. Spinning is different.
Okay, how's it different?
Because I can feel acceleration. If I spin myself, my arms go out to my sides.
So then, since the Earth is spinning, therefore we should be able to feel the spin?
We do.
How do you know that?
I don't actually feel it myself, but I guarantee we can feel it. That's, going back to what we were talking about earlier with time dilation and velocity at the equator versus at the poles. Well, you have to remember there's some centripetal force going on at the equator too. So your gravitational pull would be slightly reduced. And I know that they have verified this. Spinning is an absolute phenomenon. So someone that says the Earth is not spinning, but these stars are moving at some absurd velocity around us, it doesn't make any sense.
Why doesn't it make any sense?
Well, I mean, you're welcome to.
When I take my telescope outside, I see the stars are spinning around the Earth, and you're saying that doesn't make any sense?
No, you're welcome to claim that they are spinning.
Well, I can claim it, but it's not true, even though I can see it when I can measure it.
No, you're welcome to claim it as much as you want, but I have a feeling that you'd have a hard time coming up with a viable physical model that would account for these. If you calculate,
I don't want to get too much into this Earth-centered theory. You're going to have to go argue with the people.
Franklin, first off, here's my objection to that. I think you mischaracterized what Robert Bennett and Sungenis are saying, and miscategorized, the way you said it, you didn't exactly say what their argument is. You misrepresented it. And so I think
So
that
it's
was
very
kind of
difficult to
unfair.
represent what their whole argument is. So, like I said, you'd have to go to them to try to get their explanation, since I don't really fully understand it
Well,
myself.
I think you don't understand it, and so I don't think you should really, characterize it one way or the other.
All right. Well, let's move on to the next topic, because I know, Harry, you had raised the questions about like how solar cells work. So I was wondering what research did you do on to solar cells, and why is it you think that this is a mysterious process? Because I think that you could read in any wiki article about how solar
Well,
cells.
I've had some argument about this. Essentially, what it boils down to is you've got some high frequency energy at the vibrations at the light frequency that is converted to DC. And the question is, how does that happen? And the best explanation that I could see is that light waves are photons, and they knock the electrons out of the outer valence levels of electrons, and that causes the electricity to flow.
So, but so what is the problem that you're having with that explanation? Because that's not the.
I don't really see that it makes any sense, but hey, if you want to believe it, that's fine with me.
Well,
Well, this is the
that
way
would,
that I understand it. So let's see if this makes sense. So basically, a solar cell is basically a diode. So that current can only flow through the solar cell in one direction. And if you've ever tried it, you'll find that it's true that the leads of a solar cell, if you don't put any light on it, it basically acts like a diode. Now it works like a diode because one side of it is doped to be, like, they call it P, which is more like positive, and then the other side is doped like N, negative. So it makes it, this boundary is like a diode where the electrons can only flow from, like, let's say the P to the N. I forget exactly which way it is, but now what happens, they say, in a solar cell is that you're adding all this ambient light energy in the junction here, and that is going to randomly excite electrons, actually on both sides of the junction. But the ones that go from the P to the N are the ones that are allowed to jump across the junction, and the one from the N to the P's are not. So
Well,
it's what
Franklin, here's the thing: the process that, in order for the process to work, it turns out that you have to create a free electron and a free hole, and they have to be created simultaneously on both sides of the junction.
Well, I think that's just the basics of semiconductors. That's what I mean by the P and the N doping.
Well, but the question is, how is it that a hole gets created on one side and an electron created on the other side simultaneously? Because if they're not created simultaneously, the current won't balance.
Well, I think that is the doping, that you create regions which already have holes and regions which already have more electrons than they need. And so you create that situation basically beforehand, based on the materials that are being used. I mean, they start with silicon, and then they dope it with these other elements to either give it an excess or a deficit of electrons. So one side will already have holes. The other side will already have the excess electrons ready to go. So it's just a matter of causing the exciting the excess electrons, getting them to just by happenstance go into the other side of the junction and fill in the hole over there. And then once that happens, then if you've got the electrical circuit connected, then another electron will immediately come take the place of the one that went across the junction. And then another hole will be created because the electron has to exit. So if you have a solar cell and you don't connect it to anything, then nothing will, of course, happen. But if you actually connect a load across the solar cell so that those electrons can flow from one side to the other, then that's going to, like you said, cause the simultaneous appearance of a hole and an extra electron, and then the extra energy to get it to go across the border. Does that make sense?
Not to me.
That still doesn't make sense?
I don't really understand how it. I'm not making sense to me. I don't follow it. I didn't understand what you said.
Let's see here. Was I not clear? So you have an electron
I
on
don't
this
see
side.
how that it's supposed to cross through the junction and then pass through the load. So how,
Yes,
what
it has to
causes
cross
this,
through the
what causes the
junction.
energy? Why isn't the energy just dissipated in the junction rather than go through the load? Why is the energy
Well, the
going through the
energy
load?
isn't the only thing that's happening in the junction is the electron is migrating from physically from one side to the other.
Right. So why doesn't the energy just get dissipated in that junction and the junction get hot and the thing burn up?
Well, it would actually. If one of the curious things I noticed about working with solar cells myself is that they do get very hot, actually. And if you don't put a load on a solar cell, I believe that does make it get hotter. That so if you don't dissipate the load in the circuit, it will dissipate the energy just inside the solar cell. I mean, solar cell will quickly reach like 150 degrees just sitting in the
Well,
sun.
I think the bottom line is that if you open the circuit, nothing happens. There's no flow of electricity.
Why would you predict that? Because basically you have your diode here. That's basically a one-way valve. So all you have to do is get things moving through that one-way valve.
Well,
And
what you have is you have energy in the form of light being converted to electricity, which is another form of energy. If there's no load connected, if you have an open circuit, there's no conversion of light to electricity.
yes, that would be the case. If you don't put a load on, then there would be no generation of electricity.
Right. So what happens to the energy of the light that's impinging on the atoms?
Well, I think it goes into basically electron pressure. It's like if you have a water pump. I mean, I think electrons are very analogous to moving water in a pipe. So if you have a pump, the solar cell itself acts very much like a pump. So, like you said, if I don't have a circuit, all it's doing is creating just a pile up of water pressure on one side of the pump. But as soon as you open up the circuit, then you can have the water flow. The water can do some work while it's flowing, and then it flows back to the pump, right?
Well, that sounds like something I would have read in a electricity book from 1900 or something.
Well, yeah, that's very basic. I mean, the analogy between like voltage being like water pressure and current being like the volume of water that's running in a pipe is like very ancient, probably going back to Ben Franklin or whatnot. I'm just wondering whether, does that make sense about how a solar cell works? Or does anyone else here on the call here have anything to say about, whether what I'm saying is right? Because I'm just kind of shooting off the cuff based on my ancient knowledge of semiconductors I learned when I was in high school. So.
I think what you said makes sense. I like the analogy with water. I've heard that before. I'm confused on if we're just discussing the technology or if there um, is there some debate about, is there some conspiracy thing? Like, is there an alternate theory? Like Harry sounds like he's skeptical about solar cells, but we all know that they work, right?
Well, I think, and I was kind of wondering whether Harry knew this as well, because certain people argue that electricity is in fact not a flow of electrons.
Okay. What is it?
And they argue that electricity is actually a flow of some field on the outside of the wire or something like that. But I think the operation of a solar cell quite clearly requires the movement of physical electrons across the semiconductor junction in order for you to conceive how that thing works.
Right.
So, Harry, were you thinking that this contradicts the other people's theory who don't think that electrons is a flow of current of electrons?
I think that the explanation that electricity is the flow of electrons is just as confusing in terms of the solar cell interpretation as the. I don't really see how it can work. Where is the energy coming from? How is the energy being created?
Well, from the light.
Well, obviously, the energy is coming from the electrons, from the photons hitting the electrons, causing them to have some kinetic movement.
So the energy is coming from the force of a photon hitting electrons.
Yes.
And then what happens?
Well, that puts the electron in motion, and some of them will head through the semiconductor junction, and they're not coming back because they're not allowed to come back.
Okay.
So it's just a one-way valve.
So then that would imply that the more light that I imply, the more intensity of the light, the more current I should have, right? And I should have more voltage
Yeah.
and more energy and more power, right? But that doesn't happen. The voltage doesn't change. Why is the voltage stay the same?
Well, in fact, the current does change, right? The current, that's what changes, which is the volume of electrons that can pass through there. Now, as to why the voltage, it hits a constant, and actually the voltage will rise. If you put a little bit of light on, you'll see that the voltage will rise, but it will rise to a constant. It doesn't go past that. And I would say that's probably a function.
The voltage is defined by the potential of the junction. Okay. Now that implies that I've got to have something happening on the P side and something simultaneously happening on the N side. But all we just started with was saying that light knocked out electrons from atoms, which only basically addressed one side of the junction, and it didn't tell us about anything that happened on the other side of the junction.
Well, I would say that on the other side of the junction, electrons are also being knocked out, but that side of the junction had a deficit of electrons to begin with. So there's not going to be too much, and that the electrons on the other side of the junction aren't going to be allowed to actually go to the other side. They're going to be blocked like a diode.
That doesn't make any sense to me.
But what part doesn't make any sense?
You're just making up stuff, Franklin.
Well, I'm explaining.
You're just making it up as you go along.
Harry, do you have a theory?
Not really anything that I came up with.
Harry, do you have a theory that you're pushing that explains how solar panels work?
No, I don't have a particular theory. As a matter of fact, I haven't really thought about this for about a year or so, and Franklin's now, and I just don't really think that the photons knocking electrons out of atoms makes much sense as an explanation.
Well, it's okay that you don't understand, that you don't accept the current explanation, and it's okay that you don't like the way that Franklin explained it. But the technology is real world. Like, this is like well established. We make things and things work. We drive cars and we have solar panels, and I'm drinking a soda. I mean, you can't deny just because you don't like the way that Franklin explained it, you can't deny that this is how a solar panel.
Well, now you've changed the argument into whether or not I'm saying the phenomenon exists or not. I don't say the phenomenon doesn't exist.
Fair point.
I'm saying I don't accept the current explanation of the phenomenon.
Okay, but if we were off on our explanation, it seems unlikely that we would be able to advance. If something else was going on, it doesn't seem like we'd be able to continue to, shrink the size of our CPUs and our computers.
I don't know what that's got to do with solar cells.
Well, it has to do with our understanding of electricity in general.
Therein lies the point.
So you say that we don't understand the fundamentals of electricity, but our application in manufacturing of CPU dies and solar panels just happens to work?
That's got nothing to do with electricity.
No, but what he says is mainly correct. We don't understand the fundamentals, but the application works.
Yeah, the application works. So
we can describe what happens, but we don't understand why it happens.
Okay, but but we have one explanation which fits everything that we observe, and we don't have another explanation which fits everything that we observe. So why would we reject the first?
Well, the description can be correct, but it's not complete without explanation of the origins.
But Hans, do you say that it's fair to say that maybe it's incomplete, but is there anything left to describe? Are there mysteries that we can't explain regarding electricity?
I'll give you an example. Photons, we know that they can travel billions of light years. And photons are supposed to be waves, electrical waves, electromagnetical waves. Well, first of all, the electrical fields don't extend over such ranges. And further, waves cannot travel those distances. There must be other things than waves that constitute photons. And there are. And in fact, the explanation is already known for 2 centuries, but it's not given to photons because what constitutes a photon cannot be observed. There are shock fronts that are so tiny, so small that nothing can observe these shock fronts. But shock fronts, a string of shock fronts constitute a photon. A photon is not a wave. It cannot be a wave. A wave cannot reach that distance.
Well, we're coming up to the end here, so I don't know that we're going to solve this, but.
Nope, I don't think so. So I'm going to let's try to summarize what is going on here. So today we started off with Hans showing us a new website. Let me see. Let me get my summary up here. Let's see here. Okay, here we go. So Hans was showing us this new wikiversity.org site and how he has put up his information about his model, the Hilbert Book Model Project, up there. So this is another place for us to publish our work as scientists. And also we have the John Chappell wiki as well. If you want to have a place, you can put your work in a wiki and make sure that you have full control over the content. Then we began discussing about atomic clocks and how they work. And I think the main bone of contention is whether the cesium atom, whether that transition actually changes as a result of differences in, say, gravitational velocity effects, whether that changes. And there's some argument that actually doesn't actually change. And my main argument being that the main component in the atomic clock, which is vulnerable to these time dilation effects, is actually the quartz crystal clock, and that the cesium is only acting to lock to make that thing more stable. And we're not actually reading the atomic clock, and the possibility that if you were actually make an atomic clock based on actual atomic clock processes, that you may find that that is actually immune to any of these relativistic effects, and you would actually be detecting the actual universal clock of the universe, which is some possibility, which is, once again, only my crazy pet theory that no one believes. But there it is. That's what we're here to discuss. And we're also discussing like the effects of relativity, about whether those how that actually works. And then finally, we got into a discussion of the basic workings of how solar cells work. Since Harry had a question, I tried to give the answer I learned many years ago, back in when I learned about how basic semiconductors work. And I think that's probably still an open question for Harry. And we never did get to what happens at the load. And maybe we'll discuss that next week. But I think that will do it for this week's version of the John Chappell Natural Philosophy Society Science Chat. And we will see you all here next week, same time, same place.
Thanks, guys. Good to meet you.
Thank you, Franklin.
Now, let me see if I can get back to the conference and...
Hey, no